Well, thank you. And thank you all who have joined us from everywhere, no matter what time it is for you. We are thrilled that you are here to join and give us the opportunity for you to meet our newest robot in the Learning Resources family, Cooper. This is me. I am a curriculum consultant. I have been working with learning resources and specializing mostly in these coding experiences with students and then putting them into practice with classroom teachers. So I welcome you to feel free to put it in the chat if you have any ideas, want to have conversations. Please use this as an open forum for us to use this as dialogue between educators. So you'll see on the screen a few of the 21st century skills that can be taught through coding. As we know, there's a huge movement to get kids off of our devices. However, on the opposite end of the spectrum, there's also preparing our students to become those computational thinkers that have to use these technology pieces in the real world. So using devices such as these Cooper robots will allow us as the educators to balance this shift. So we're going to talk through why Cooper is effective in these 21st century skills. You'll see on the screen a screen-free coding experience. And what does that mean? Screen-free coding experience provides experiences to all age learners to think systematically and to design solutions through trial and error. Take a look at this picture on the screen. This was a screen-free coding experience. I've used experiences such as these with children and educators. In this particular opportunity, each person had matching pieces and a grid. One educator built the city, one had to communicate their build or program to another while keeping the city hidden. The partners were not allowed to ask questions of each other. They were not allowed to show each other their design. At the end, we then asked them to reveal. You may be thinking, how does this relate to screen-free coding? Well, when we teach our students, the hardware such as computers and robots only can perform programs that we write and communicate. If you've ever taught coding, think about how many times your students say to you, it's not working right. That's not what I told it to do. We have to communicate in a language that our computers, robots, and other humans understand. This is the basis of these experiences. So why Cooper? If you've been around the learning resource family, you've known that there are many robots to choose from. In our buildings, we have grown along with this company and now use all three of these products you've seen on the screen. We've created integrated curriculum and banded each device by grade level. We start with our pre-K first grade learners using the Code and Go robots. These robots, such as the mouse, have 4 directional coding buttons and travel in straight lines. As we move into grades 2-3, we introduce coding with Botley. This robot has a few more features due to its size and its ability to push or pull objects while being coded using a remote control. And now we have adopted Cooper into our classrooms. This robot has capabilities to interact with each other, with objects in the environment, and allows us to introduce coding such as if-then statements. The ease of learning and integrating any of these robots, however, can be used in any grade from pre-K on up. In our time together, feel free to come off mute, ask questions, share ideas, solutions. Our goal tonight is to show you Cooper so you can meet him, explore the components, show you some kids in action with the robots, and show you lessons that are pre-made for teacher support. I introduce to you Cooper. He is the classroom cooperative coding robot. This on the screen is our classroom set. All that you see on the screen does come with a classroom set. We're going to talk about each of these components and how you can use it in a pre-K-5 setting. We're going to unbox what Cooper actually looks like. This video, you will see the classroom set and all of the components that come with it. Everything about the set was created with intention to use in a classroom setting, down to the fact that the box actually becomes the storage for our robots. Another conscious decision by the developers was that all 4 Cooper robots charge from this one USB device that is included. I don't know about you, but this solution is a game changer for those of us in the classroom with limited space and outlets. The classroom set also comes with 20 challenge cards that are scripted. I've been able to leave these robots with pre-made lessons with substitutes and provide them for my after-school teams to integrate into their time. We're going to look closely at how these lessons are all designed. And have no fear. As the educator, I always tell my peer, it's okay for you to not know everything. It's okay not to know how to code or program our robot. Our craft and our skill as the educator is that facilitation of learning, that ability to question. This activity guide comes in this classroom kit. It provides us with support and back pocket coding questions. Now on the screen, you can see an individual Cooper and the features that make this advanced coding tool a success for the K-5 student. Notice this Cooper and robot has an advanced sensor technology on the front, different from all of our other robots that we've used in the past. This allows Cooper to interact with each other as well as with the environment. I will tell you, those rugged wheels really are rugged. Our students have run them over all sorts of things, and our Coopers are still lasting. Cooper has 4 directional codes. When purchasing the class set of Cooper, you also receive the cardboard cards to allow students to manipulate programs prior to pressing play. These lessons are only the beginning of the screen-free coding experience. In our classrooms, K-5, we require students speak the program in human language, the pseudocode, before we ever press play on the device. We start by looking at the coding blocks like you see on the screen. You are welcome to come off mute or put in the chat what you think each Cooper block or color block means. Those of you from the elementary world realize how precious instructional time in the classroom is. I've utilized Cooper to integrate coding into the content areas. We do not have the gift of specials or being a STEM school or computer science time. However, we know it's critical to expose students to these standards. In both science and literacy, identifying the difference between observations and inferences is a skill across the grade level bands that students can consistently struggle with. We utilize these opportunities to ground our students in the academic language. So I see a couple of us have put into the chat what we think they might mean. So I see Emily has shared that she thinks the orange may mean Cooper needs to go up, purple down. And when we ask our students, we look and make these or we infer what they mean based on those observations. Okay, so I'm going to infer this might mean go up, as Emily is saying, because the arrow is pointing up. So I'm going to show you what that looks like. We use this tool as an observations versus inference task in the classroom. Yes, you can see Cooper's movements of forward, 1 space, backwards, 1 space, rotating right and rotating left. However, we don't tell our students that. They need to explore. I'm going to let you see how my students started exploring those Cooper coding cards. So we've got some coding cards right here.
Yeah.
What do you infer this one might mean?
Maybe jump this way.
Jump which way?
That way.
Okay, why do you think that? What observation helps you think that?
Because the arrow is showing up and sideways.
Okay,
This way.
so you think he's gonna jump?
Yeah.
Okay, what about this one? What do you infer this coding block would mean?
I mean, I feel like it means that it goes this way. The robot goes this way.
Okay,
And because of the arrow pointing to that direction.
so you observe that the arrow is pointing that direction. So you can see how we are able to integrate some of our scientific and literacy language right into the use of this robot, and students start to explore and create some meaning of these Cooper coding cards. Again, we have not told them what these meanings are. Those are our back pocket answers for us as the educator. So we've got some coding cards. So how do we read these programs? Once students have learned the meaning of each of these coding blocks, the coding cards line up together like a puzzle, and they're read like a scratch program from the top to the bottom. As students continue to write programs, we do talk about how to make the programs more efficient. So on the screen, you can see that our expectation for this Cooper robot would be to move forward, move forward, move forward, rotate, move forward, rotate, rotate. Now, if we ask our students to make this a more efficient program, we can use just 4 of the blocks and start talking about some repeat functions and some loops. Again, students and educators, as you look at this image, you should be able to communicate the program in human language before ever pressing play on the robot. The image you see on the screen is adult learners acting out the program that is being read to them to ensure their program is correct and understandable before we press play on our robot. Again, another screen-free coding experience to allow students to have that thinking and that iterative design process if their program does not work. By acting it out, students start identifying and debugging their own programs, again, completely screen-free. You just created.
Circle.
I apologize.
The other side.
So I want you to stand up. I'm going to give you the program you just said, okay? I want you to go forward 1 spot. I want you to turn right 1 rotation. I want you to go backwards 1 spot.
So as you can see, by us reading the program out loud in human language, the students start adapting and realizing where their errors were in their program.
You just created.
So then we get to move to the robot. So we're going to see the robot act out that same program that students created. Students first wrote a line of program to get Cooper from the starting point to the stopping point. So now students have had multiple opportunities in order to read program, understand code before ever touching the robot. And then they can decide if their success was the fact that the robot was moving in that correct program or the correct way. So as I noted earlier, each classroom set comes with task or challenge cards. There are 10 cards that students can use with only 1 Cooper and 10 cards that require students to cooperate using multiple Cooper robots. When we use these in our classroom, we tend to put 2 students on each device. All of these lessons come in that Cooper pack as a cardboard plastic covering so they can be utilized over and over again. And we're going to look at those up close. We're going to take this guided walk through an independent lesson. You'll notice that all of the task cards are set up similarly. The title, objective, scenario, and challenge are all written in student-friendly language. So on this one, we are looking at Cooper on surfaces. You will see that the students are to design a test to collect data on how different surfaces affect Cooper's speed. Okay. It also gives us a bit of a storyline or a challenge that they are going to have to solve in order to determine the speed of Cooper on these different surfaces. As we continue looking at the support, you'll notice that the task lesson cards call out the skills the students are going to focus on. In this lesson, the computer science skill is the actual programming of Cooper. Okay? It is the iteration of how programs can change, how programs look different on different surfaces, and how Cooper may or may not react the same every time we press play on a different surface. You'll also notice some lessons suggest some additional materials. This one does. For example, we do need our Cooper robot. If we're testing different surfaces, we need different surfaces. So there's some suggestions such as the tile, your concrete, grass, or carpet. So it can be done in the classroom or at an at-home experience. There's some additional measurement tools such as your timers, your yardstick, any kind of measuring stick. And we're going to talk about what that student recording sheet may look like if you opt to use it. In the upper right corner, you'll see that the Cooper lessons also timestamp the amount of time it would take for the lesson to go through its full iterative process. They all can be adapted for shorter class periods or longer, and these lessons were vetted and timed with grade 3 students that have never had coding experience. So the lesson time frame itself on the higher end allows for the entire data collection, a conclusion, and connections to content. And again, we'll look at what that student reflection sheet looks like if you opt to utilize that. Sometimes there is a bit of teacher prep. For example, if we are trying to measure speed, we need to ensure that the distance is the same for each of the surfaces because students are ultimately measuring the time it takes for Cooper to travel over these surfaces. So the teacher prep might be to measure out the same distance on each surface. Again, these are adaptable. You can change this however you want into the classroom setting. All of the lessons are set up in 3 components: a plan, a try it, and a conclusion. You'll notice within each of those sections, there are teacher supports to allow questioning, connections to data collection, content area standards integrated into these challenges, and supports of how we can probe our students. I know it's small on the screen for many of you, but for this plan, the plan was for them to, number one, record what was the problem in our own words or pictures. Again, thinking that screen-free coding experience, can they think through the steps of what the program is going to take for Cooper to travel from point A to point B? Okay. Then there's always a discuss. There is either a discuss with students or a turn and talk with other partners. This way, this one is talking to students about the best way to collect and compare that data. So it gives us as the educator some of those back pocket answers or anticipated responses, such as you might be measuring the time it takes for Cooper to travel from the start to finish. You might just use 2 surfaces if you want them to measure distance instead of time. So again, whatever it is your focus is on, remember the way this is written is to focus on the programming of Cooper. Okay. And then it continues on with questions we can ask and questions that we can leave students thinking about. Example, determine if we need a sensor or ability that Cooper will need to complete the task. Okay. And then we allow kids to program and try it. On each lesson card, there's also a section called personalized learning. This gives us some differentiated strategies for students needing additional support or if we need to extend the learners that complete the task quickly. So this one is actually going into some of our scientific processing skills of how we can create and test procedures and discuss what makes fair tests, as well as having students walk out the code. So again, for both our students that are struggling, as well as those that need to be extended. Lastly, on each card, you're going to see a QR code. Now I know it's small on this screen, so I'm going to show you what this QR code links to. It's linked to our Learning Resources platform. This is where there are some included printables that teachers can use, home parents can use in order to track the data or the coding experiences that they have with each of these lessons. So when you click that QR code, it takes you to this platform on Learning Resources. You'll see that there's an area for student recording sheets. These are aligned to those lessons that come in this classroom set. You can opt to print them. You can opt for students to put them in their notebooks. This one happens to be the one for Cooper traveling on the different surfaces. So you'll notice each of the recording sheets always gives students a space in order to do the problem or challenge for them to come up with what it is they are trying to solve. Okay. Then we go into the planning section, and then we go into the try it. On the second side, there is always a space for students to record their program, write it out, and think about it. There's always a section for them to also put that program into that human language or the pseudocode, what they expect the robot to do. Then, if the lesson is supported and needs a data collection table, you'll notice that there is a pre-made data collection table that students can utilize. And then it always concludes the lesson for them to think about what claims they can make based on what they've experienced. So I'm going to show you some of what it looks like with students. Again, we just took this outside. The robot is just on the concrete, and this was just for them to start exploring. Maybe. There we go. Sometimes I like the controlled chaos, and you will notice that we have adapted this lesson into creating our own surfaces. This was an attempt to keep the classroom in a specific area because we know what that looks like when we take students outside. So we created our own surfaces so that students had a controlled experimental testing location. I'm going to show you what that looks like with them actually moving on these surfaces. Each Cooper was programmed with the exact same sequence of steps. Students can make observations of the movement, the speed, the distance, however you frame this lesson or wherever you are trying to get students to that end goal. Students should be able to make some observations about the way Cooper moved, how he traveled over the different surfaces. If it was the same program, one would expect that you would travel the same way. And students start to make some of those observations of like, wow, I wonder what is making Cooper turn a little bit. Wow, I wonder why he traveled further on the red surface versus the bubble wrap surface. So this is where it gets into the power of using Cooper into the classroom. So as I stated before, our goal in the areas in which I work is to utilize our classroom coding experiences within the content area. This was a perfect connection within the science curriculum with our students. So based on what they did, they created wonders, and we added that to our typical science wonder wall. And these coding experiences led students to open inquiry projects and ideas for their own STEM fair projects through these wonderings. So our big initiative in our district is to use these robots as much as we can within the content area. This is the same surface lesson became the engage to then provide students to ask their own questions. They started asking about what surface would Cooper move the best on? What effects does the surface have on the speed? Why does Cooper's movement change on each surface? And this is kid language. Okay. They then were able to develop questions and data collection about friction, speed, measurement, and observations of movement, all things that tie into most people's curriculum. Okay. The surface lesson could be done with just one Cooper, but there are 10 lessons that are designed to have Coopers interact with one another, such as like the relay race. You can see that this lesson, the focus is on object detection. When Cooper gets to the next robot in the relay race, they must pass off a baton for the next robot to travel. All of the cooperative lessons are designed to encourage that teamwork and collaboration, not only between our engineers that are programming the robot, but also the robots themselves. And that's what makes Cooper that standout robot versus the other devices we've utilized in the past. This is another example of a cooperative lesson that includes a design challenge aspect. And I included this one for the fact that not only does it include that design challenge aspect, but it also is a math-centered focus. Okay? Students are asked to create a device to allow Cooper to hold a writing utensil. Then program Cooper to draw a two-dimensional shape. So we have the engineering aspect of them having to create something to hold a pencil that will actually draw, and then they need to program and know what the physical properties are of that two-dimensional shape. Then, after they get theirs perfected, they have to share that program and that algorithm to another set of engineers so another Cooper can replicate that same program. Again, giving them experiences of what engineering could look like using this device. These are just a couple of the videos interacting with this actual lesson. In the first video, you can see we are just starting off using that think sheet, which again could very easily have been put in the notebook. But I want you to think about how we could tweak this and use it in a math science classroom and thinking about the academic language that students are utilizing, even just as they speak when they've been given that problem or challenge.
A 2D shape.
A 2D shape. It has two dimensions.
Two.
It has length and width.
Very good. So in the first box, it asked for a problem or a challenge. Go ahead and decide what 2D shape you think that your robot can draw.
Maybe like a square.
What do you want your robot to draw?
Wait, let's do a pentagon. Let's see that.
I love it. Let's do a pentagon and let's see what they actually come up with. So when you look at the second video, you will see how students had to engineer this way for them to hold the pen and then program for their 2D shape. And you will see the excitement of them completing a shape.
We could do a small circle like this. Oh, no, do the square. Look, it's touching now. You can do the square. The star.
Oh, you made a star.
We got a star, guys. Woo! We got a star.
So we're not going to say that's their pentagon for, but they knew that they had to go back to that design process because they knew that they couldn't replicate that or share that program to another set of engineers. However, they were really excited that they got this star. So again, just looking at this lesson with a couple focuses of how we can engineer or create that way of holding the pen, as well as what are the different programs and how can we communicate those programs to other groups of engineers.
A 2D shape.
We could do it as two dimensions like this.
So Cooper also has some interactive features that allow you to program one Cooper and allows the other Coopers to react to that Cooper's program itself. So I'm going to press so you can see how one Cooper is programmed and the other three Coopers are going to engage back with that first programmed Cooper. Our symphony for us that students will learn how these can communicate to one another. These ones are programs that are pre-given to us as the educator. So before students have to learn to program for them to communicate with one another, we start with the basics of let me give you the program so they can see that there is a communication mode. On the back of this Cooper, you can see that there are 4 buttons. So we talked about the 4 directionality buttons on the top. These are the 4 interactive features to allow Cooper to be cooperative with one another. And we'll look at each one of those independently, but that's where they are on the actual Cooper robot themselves. And they are on each one. So you can choose for any of the Coopers to be the main one that you program, and the other 3 can respond. So here's another response and them communicating. Notice some differences in their eyes. Their eyes turn when they communicate, and then those sounds are the communication sounds that they talk to each other or communicate to one another. So these are those buttons on the back. And these buttons can be utilized in a variety of ways. And as you are scaffolding the lessons or as you are scaffolding experiences for students, you'll give them opportunities to do them at their basics, where one Cooper can do it by themselves or cooperate with one another. And then they start utilizing these when they create programs and those algorithms that are a little bit more intense of like they have to do if then statements or create a maze where it has to detect different objects. So our first feature on the back of Cooper is this black line following. You can draw any black line and you can program these Coopers to follow this black line. I'm not sure why my students get such a kick out of that one. However, that is one of their favorites because they draw all of these mazes around the classroom in order for Coopers to have to follow after the human follows them. So that is one of the highlights in a classroom for whatever reason. There's also on the back, again, these are coding cards as well, those cardboard cutouts that are included in that classroom set as the students are creating that sequence of codes in order to create that program. So you'll see that Cooper also has a communication mode. So these are the 2 Coopers communicating with one another. So the Coopers think they're funny. They also tell jokes with one another. They also have 2 additional features, one being the light sensor, which is really cool when you create a maze that has tunnels or where Cooper has to go under different objects. And you can ask the students to program in order to, when he goes under the tunnels, that the light sensor is detected. And so you can see his eyes actually change when it gets dark. As well. The one I use mostly in grade 4-5 is our object detection because at this point in our scaffolded way in which we've written our coding curriculum as well as our integration within content, Cooper does a lot with object detection because we talk about if-then statements. So this is just Cooper, if he bumps into something or notices, recognizes, sees an object, he's going to do something. Okay, and this is Cooper doing it. And there we have Cooper detecting different objects, which is critical as the students start getting into more of the more sophisticated engineering solutions. So I did see a couple questions, and I'm not sure if everybody has the chat open. The line does have to be a certain thickness. It needs to be a minimum of 6 millimeters thick. So many of our just regular black markers, the students can just draw on anything. I have found that it is most effective on a white surface and the black marker for them to detect it the best. But again, another thing that the students can test and check out and see what works for them. So Cooper also has some bonus programs, and these are fun, and they're in the activity guide for educators. So you'll see that it's a sequence of the coding cards you put together, and Cooper has some pre-programmed, um, different fun activities that Coopers can do. So there's one for pets. Like I said, comical Cooper. My kids will just giggle over and over again because we have him tell jokes. And this is the code in which you put in, and Cooper will tell jokes, and Cooper giggles back to each other when they communicate. So we're going to look at a couple of those bonus features. Again, just a fun aspect. I see in the question in the chat, is the communication on by default? On the back of Cooper, there are 4 buttons, and those buttons you have to press and let it be inset. You'll notice when it's pushed all the way down in order to get them into these different modes. So here's Cooper telling a joke. So you're all going to laugh at our Cooper's joke because it's really funny.
Do you want to hear Cooper tell a joke?
Single time. So again, that's a pre-programmed one. The students are not doing any kind of thinking with that one. Again, it's just trying to get them to see how they can start communicating and with each other.
Do you want to hear? Do you want to see the Coopers do some real cool dance moves?
So again, this is the symphony one. I kept this here because at the beginning, student actually coding the orange one in order for the other Coopers to cooperate or communicate back. But at the very beginning, see if I can slide it back, you can see the buttons on the back. The blue buttons have to be pushed in for them to communicate if you want them in communication mode. So they're not always in communication mode. I guess that wasn't the best slide.
The Coopers are going to communicate.
There's one more that Cooper does a cat and dog chase. Them right off of our mat. But yeah, so the kids get a kick out of that. This is the first we introduce them into that communication mode of how to get them to work with each other. And we know that once they see the Coopers start communicating, they themselves start communicating as engineers. And we do know that's one of our 21st century skills. It is in our computer science language. It is in our science standards that communication is a skill. It doesn't matter whether we're pre-K or up to 5th grade. They do like when they see the Coopers communicate, and it does start translating into the work ethic and the work between the partners. So these are all some fantastic features, but we also know in the classroom, in order for us to ensure usage, that we have to have some kind of integration and alignment. So on the teacher resource page, there are some standards alignment documents if you need to share them, if you want to look at them. They are aligned currently to the NGSS science and engineering practices, as well as our computer science standards from CSTA. So that gives you a little idea of like, if you selected one of those pre-made lessons, what skill set you are going to utilize. Now, again, when you're thinking in the world of education, all of these can also be integrated into your literacy block, to your science block, and your math block. And so we've been able to take these concepts and take each of these lessons and scaffold them throughout our curriculum calendars so that the students are using a robot about once a week in one of their content areas, in their core content areas. But again, going back to the fact that it's an engineering design, or going back to the fact that they are learning some kind of computer science standard behind it. So these documents are there and printable. So overall, as we move through learning and meeting Cooper, You should have seen that we were able to use Cooper without any other additional devices. So teachers don't need to have another computer. All they need to do is be plugged in with the USB cord, get a charge, and then they are free to roam around your classroom and start coding. There are those included lesson plans on the teacher resource page. Everything is a printable document. So I will say, like, for example, like the coding cards, I'm just going to hold them up for those of you that also have your screens on. The coding cards we've been able to use in the classroom. My students now have them printed and we laminate them. So every student has a set of coding cards as we move into like, let's think independently before we come back and brainstorm as a partnership. So those are in there as well as being printable. All of those lesson plans are printable. The data collection sheets are printable. And some additional programming aspects are printable. Um, and then we do know that out of as the robots have grown within the learning resource family, this robot has some of that technology to allow us to have that communication, to allow them to do some if-then statements and some iterative design with the capabilities of his arms. I don't know if you notice his arms are flexible. They have little pinches on the end. There are some lessons where it holds index cards and it carries different masses across areas. So they're indestructible and students can utilize them and position the Coopers in any way, shape, or form. Um, so we've really enjoyed actually putting them into practice into the classrooms and starting to integrate them into the curriculum. That way we have that grade level band. So I'm going to pause before our time ends. There is a QR code on the screen to allow you to get to that teacher resource page. There's also an email on there if you have any burning questions about Cooper. But I also want to give an opportunity for any question and answer in the chat that we didn't get to, or share something that you've done that you know works well when we are integrating these experiences for students. So I'm going to open up the mic to our team.
I do have a few questions from the chat.
Awesome.
So I want to make sure that we get those answered. So someone asked if there is a color coding system to the cards. Just to clarify, there's no real system to the colors of the cards. It's just that each direction has its own color. So another question that came up is, when do you teach, Michelle, this is for you, when do you teach them, your students, the word algorithm?
Oh, I love it. Well, I failed to say that I'm in the state of Florida, so our science standards or our computer science standards are a little bit different. But we introduced that all the way down in pre-K after they've learned that that string of code then creates that program, and then that program becomes our algorithm that we can share. So we have academic language walls that students, when they use any of our devices, are expected to utilize the computer science language of pseudocode. They're expected to utilize the language of a coding block, and then algorithm and program. So that's a good question. It is not on the teacher lesson pages. It just has them doing the coding cards, then creating that program, and then writing a pseudocode, writing it in human language. But that was a good question. And I would love to like work with whoever is doing that, what you're doing in your schools too.
Another question that we had is, what feedback have your students given you about learning with Cooper?
So we've done some anecdotal researches when we utilize the robots in the classroom. Our grants and research department has worked closely with us in our district. And obviously it's anecdotal in the sense that we are trying to outfit all of our schools with some kind of devices. But the anecdotal records of this research has come out that our attendance increased, knowing that they would have an opportunity to utilize them. I noticed in the science world, that's where I handle most of our integrated lessons in the science classroom, that students have the ability to question more because they've had something concrete to play with or explore with. Then they come into that open inquiry and they actually ask valid wonderings. I know we always ask kids to ask questions, but these ones are actually focused on the content I'm trying to eventually get them to. So every time we pull one of these out, the students always are excited. We keep them in centers, and it tends to be even when we have optional resources that, or recess, excuse me, our students tend to go to our devices to play with in some freedom and let them just explore with them and play. So I'll say that in a K-5 environment, there hasn't been one class that we're like, oh, they didn't really like using these. But again, we've used it to infiltrate and embed it into our curriculum. So
We have another question. I think we may have covered this or you may have answered it,
okay,
but if not, I'll just
that's okay.
read it out for the group. Someone asked about the lines, if they need to be a certain thickness. And so the lines need to be a minimum of 6 millimeters.
Yep. Yep. And almost all of our black, like the Mr. Sketch markers, or almost all of them are thick enough. So, and it detects those lines. Yep.
I think that covers all of the questions in the chat. If I missed any,
Please
let me
don't
know.
mute
We
or
can,
share. Yeah.
yeah, we could take you off mute if you'd rather speak the question, or you can put it in the chat and I can ask Michelle. Well, it looks like we have no further questions. Um, thank you, Michelle, for your time. Thank all of you for your time. There'll be a short survey after the webinar, and it will also, I think, be emailed to you. And then once we have the recording up, we'll send out the link to everyone that registered for the webinar.
I mean, I should have been crafty for Cooper to say goodbye to everybody. However, Cooper and I thank you for your time. And those of you that are on here, I would love to connect and see what's happening in your buildings and share our ideas.
We have one more question. Can you
Uh-oh.
program a different set of eyes on each Cooper, or do they each come with a different set of digital eyes?
Ooh, we may have to go to an expert on that because I do not know that. I know that eyes do change and they all don't have the same eyes all the time. Maybe there's an expert on the line.
Each
There we go.
robot,
Each
yep,
robot does have a specific set. That's why they
yep,
appear differently.
they can't be changed. Good to know.
That's a good observation I should have had.
Everyone, have a great evening. Thank you again for your time, and we hope to see you again soon.
Thank you all.